can raise this a little bit here. No, there it's on now. I don't need a pointer. We're going to have Viv's going to be doing the slides, and I've got a document here. Anyway, morning everyone, and thank you, Patricia, for the eulogy. I think some less kind people would say, Rob, you actually kicked yourself in up and under by supporting the SKA Project then and then going in and directing it 10 years later. So that would be another way of looking at what happened. But back to amateur astronomy. When George Miley, a professional astronomer, he was the founder of UNAWE, which is the Universe Awareness Program. When I see the letters UN, I always want to say United Nations, but in this case it's not that. When he addressed the SAO here during his visit in the year 2010 for the Communicating Astronomy with the Public Conference, he stated that the amateur community were the bedrock of outreach. And you're the people at the coalface, not the administrators, educationists, professionals, scientists, etc., who make, even though it's not a good living, they make a living out of writing and talking about outreach. But those like you who turn up night after night for no money, with personal, valuable equipment to share your knowledge and connection with the night sky. Radio astronomy, however, adds some complications for amateur astronomers, in that it's much more technology-based, more difficult to grasp, requires equipment, props, knowledge that amateur astronomers don't easily have access to. It's also perceived to have a heavy technical bias towards signal processing, and the very images themselves are a fiction. They're a visualization of signals that are beyond the senses of humans. And so, in a way, we're looking at something which doesn't exist when we see a radio astronomy image, because we can't see that. It's exciting, for example, to imagine an experiment to detect the first stars in the universe switching on. That was a Nature paper in the last week or so, where tentatively the Murchison Wide Field Array people have managed to see the epoch of reionization for the first time. But it's difficult and confusing when we hear that we're not actually seeing the stars beginning to shine. We're detecting an effect that an ultraviolet photon stimulated electron transition has on the redshifted H1 line via something called the Vogt-Heisen field effect. So try and catch the public with that one. There are a whole series of steps along the road to there that you lose most people, and even physicists and astronomers. So with radio astronomy, the public interest therefore tends to be generated by the technical and engineering prowess and scope of the antenna arrays, the high-tech backends and the mind-boggling amounts of data, high-performance computing that lies behind the science, because you can't actually see anything. And Bernie Fanaroff, my predecessor, used to tell a joke, a story, when he was in the trade union movement many years ago. One of his close comrades was Alec Irwin, former minister of various things in the Mbeki government. And they would stop driving from long distances from one town to another, organizing workers. And Alec would say, Bernie, since we stopped here, tell me a bit about the stars up there. So he says, Alec, I don't look at the stars, I'm short-sighted, I listen to them. That's radio astronomy. There's been an increasing focus on multi-wavelength astronomy, and what's more recently known after the LIGO and Virgo evidence, multi-messenger astronomy, because astronomy now goes beyond electromagnetism towards gravity. And it's evidence for increasing convergence in physics, and the multi-messenger approach gives us a whole new set of tools to piece together our understanding of the universe. But my presentation today we'll be looking at the history of the SKA. Patricia's in a way stolen some of my material. Our involvement in it, my view from the other side of some of the events that she described, what type of research we can expect from Meerkat, and then something about public outreach, our experience with a recent implementation design called the Multi-Wavelength Astronomy Public Participation Program, which is about designing an outreach program on astronomy for the public. Okay, SKA. Big radio telescopes around the world were mostly built in the 60s through to the 80s. Understanding that it would take 10 to 20 years to build the next telescope, scientists started asking themselves, well, what's next? What do we want to build? And so from the early 1990s, people like Peter Wilkinson in Manchester, Bron Eakers in Australia, started discussing this and decided they wanted a telescope that would be sensitive enough to see neutral hydrogen right back to the universe becoming transparent to radio waves. In other words, the beginning of the Dark Ages, approximately 300,000 years after the Big Bang. Before that, you can't see anything because it's all ionized and no light gets out. You can't see any structure. They then worked out, somewhat incorrectly, I think, given the increase in sensitivity that's come about since then, that such a telescope would have to have a square kilometer collecting area, and hence the name square kilometer array. The initial specs were a bit unrealistic. Nevertheless, at that time I was the Director General of the Department of Science and Technology, and Patricia said it's arts, culture, science and technology. I always forget when we made the transition from the one to the other. It was 2002, but I think the bid permission came after that from Cabinet, so I think we were actually science and technology then. Anyway, in those days, we had the privilege of being able to design and instructed to design South Africa's post-apartheid science policy. South Africa just emerged from an era of sanctions, which included an academic boycott. And so we asked ourselves the question, well, okay, which areas of scientific research in South Africa offer a geographic advantage? In other words, which areas are likely to attract either large international infrastructure or large direct investment? And so, you know, it's kind of a brainstorming day or so that we had, and we came up with 5 or 6 areas, one of which was HIV/AIDS. And I mean, that has a long, I won't go into all of the reasons that didn't quite succeed, and the wrong decision was taken at another level of government. But clearly that particular challenge that we faced as a country, that we tragically faced, posed scientific challenges to highly expert scientists in other parts of the world. And so that was an area where our interests could converge and we would get investment. To cut a long story short, one of the other areas that we felt that we could be competitive in was astronomy. Well, why is this? Well, first of all, Northern Hemisphere astronomers, unless you work with neutrinos, need observatories in the south because you can't see through the Earth. So it's kind of obvious that you need something in the south. But why Southern Africa? Well, I'd seen how it worked in Chile and Australia. I'd in fact been part of an international team to look at the science and technology system in Chile because they were interested in getting Inter-American Development Bank loans for new national facilities, science infrastructure, and so they had to have a study, the bank said, of their system to underpin their investment proposal. And so I spent 6 weeks in Chile and was then able to see how that very large international astronomy investment was deployed. And when I looked at it, I thought that we can do better than this. It's changed a little bit in Chile now. There is more interaction from the Chilean science system. But at that time, you had 2 systems in Chile. You had this big international deployment of very sophisticated, costly instruments, and then you had everything else, which didn't really touch on the astronomy much, and was run at a much less sophisticated and smaller scale. And I felt that given our own scientific capability, and in particular the engineering competence coming out off the back of a strong defence industry, we would be able to assist in design and construction to a much greater extent than the Chileans had been able to. So that was where we were then. And so the decision was then taken to position the Southern African region as a hub for astronomy. Thus the hosting of the Gamma Ray Observatory, Hess in Namibia, the optical Southern African Large Telescope, SALT near Sutherland, and now the radio telescope, square kilometre array, approximately 100 kilometres from Carnarvon in the Northern Cape. They were all consequences of that original strategy, which was based on asking the question, how can we attract to our country significant international investment in science infrastructure? The National Research Foundation under Khotso Mokhele then took up the challenge as described by Patricia of making this vision leap out of government PowerPoint into the real world. You know, it's kind of easy in a way to brainstorm something and then come up with some ideas, but then making it real, that's another story. So first there was Khotso and his team of Gerard van Groenewalds, now tragically passed away. Bob Stobie also passed away, who was a former director of the SAO here too. George Nicholson, and then Justin Jonas, as previously mentioned by Patricia, brought SALT and Hess to us, and then the SKA. Hess is located in Namibia, and thus no South African cabinet level decisions were required. However, SALT was taken to cabinet in 1996, and I still remember, in fact, going in and making that presentation. And then what happens in cabinet meetings as an official to you is you then, once you've made the pitch, you get asked to leave. And you go and bite your fingernails outside. And I then saw the doors maybe half an hour after having given the presentation. I saw the doors swing open, and then Minister of Finance, Trevor Manuel, come storming out, and he wasn't at that stage, he changed. He wasn't at that stage a great supporter of science investment. He changed over the years to become one. But he glared at me, and we knew each other quite well. He glared at me and gave me this sort of look, and he said, "Ha, salt, I won't even give you sugar." And at that point I knew we'd won, you know, because otherwise I wouldn't have come through like that. And you know, the person who really was instrumental, Patricia said it was me and Khotso, was actually former President Mbeki, who as Deputy President then chaired that cabinet committee meeting, and apparently when the topic came up said, no, let's move on, we already agreed on this. And then he just moved on to that's apparently what happened. He just essentially said, no, this has been agreed, and move on to the next topic. So that was the SALT discussion. And then we took, you know, by the time we got to take SKA there in 2002, the ground was already very much softer, much easier to plant in. And also, just the vision of the SKA was easier to sell. It had this tremendous sweep. You know, with an optical telescope, it's just one 11-meter lens, a set of mirrors here in a building. But with a radio telescope, particularly the way that we portrayed the SKA, as this tremendous sort of spiral sweep of antennas going up through the African continent, huge data flows, involvement of other African countries, etc. I mean, that was very compelling. And I think my answer to anyone, and there were many critics of South Africa investing in astronomy, my answer as Director General at that point to those making those criticisms was, this is a compelling vision. It's not taking your money. The money that's coming into it would probably go to Home Affairs or something if it didn't come here. So come with your vision for what you want to do. Don't knock somebody else for having a vision. And I think it's not always a zero-sum game with money. Sometimes there is additional money. If you don't have a big picture vision and bring something new, then of course it is a zero-sum game. But anyway, on to describe this in more detail in terms of the SKA. In particular, there were other government departments, Foreign Affairs, Communications, Trade and Industry, that were very enthusiastic about it. And Foreign Affairs in terms of the impact on the African continent, Communications because of the data traffic and the excitement on that front, and Trade and Industry because of particularly the high-tech, the impact on the high-tech sector in the economy. So after discussing with Kgotso Mokhele, I then called Bernie Vanneroff, whom I knew in other capacities. Obviously I knew he was a radio astronomer. We needed somebody who could understand government and also could command the respect of the astronomy community. And there was nobody else, frankly, at that time who was in that position. It was a unique chance that we had to convince him to be part of the project. And so at that stage the team consisted of Bernie, George Nicholson and Justin Jonas, just the three of them. And of course me as their principal running interference for them in the government. But since those fledgling days, we've grown to our current a bit more than 300 engineers, scientists and administrators. So it's been a phenomenal growth. Later, Bernie and Justin recruited Anita Lutz to the project, very influential in the early days. And she put together a team of engineers that spoke to Professor Mike Ings at UCT, who introduced us to the concepts of system engineering, which became a key feature of the way we do things in the South African part of the SKA project. So we started off as a telescope project, was ultimately pursued as an engineering project, rather than one run mainly by scientists, which is typically the way that it can be done in other places. Like we've had our chief scientist, Fernando Camillo, come to us 2 years ago, and he said the difference between you guys and all the other places I've been to is in all the other places you've got a bunch of scientists faffing around pretending to build stuff, but you're running it like a proper engineering project, which is in fact how we've managed to get, I think we're probably the only telescope, I could be wrong Patricia, that is actually performing better than spec. Most other instruments perform worse than design spec. Ours in most areas is at least 30% better. So before we go further, and in case not all of you are completely up to speed, I need to answer the question, what is the SKA? Why is the SKA? Where is it? And who's part of it? And et cetera, et cetera. So it's an international project to build the world's largest radio telescope, up to 50 times more powerful than any existing facility. The scale of it is a huge leap forward in both engineering and research and development, making it ultimately one of the world's technologically most advanced scientific facilities. As one of the largest scientific endeavors in history, SKA brings together a wealth of the world's finest scientists, engineers, and policymakers. It will be able to conduct transformational science, breaking new ground in astronomical observations to investigate, first of all, Einstein's theory to its limits using pulsar techniques, how the very first stars and galaxies formed just after the Big Bang, something I described earlier on with the MWA precursor. Then dark energy, the discovery of which gained Brian Schultz and others the 2011 Nobel Prize for Physics. Powerful magnetic fields which permeate the cosmos and that we don't know the origins of. And also whether we're alone in the universe. Is there not just other life, but other intelligence out there? South Africa's Karoo region and Western Australia's Murchison Shire were chosen as co-hosting locations for many scientific and technological reasons, from the atmospherics above the desert sites, radio quietness, etc., etc. And I think, if we were to be perfectly honest, the Australian site, from a pure radio astronomy point of view, is a better one. It just is more radio quiet. However, it's so good that it's very remote, making it very expensive. And you know, you want your site to be remote, but if it's so remote that it costs you an arm and a leg to get the power in and put the roads in, then you know, you want it to be slightly less remote. And so it's always in the end, it's always a compromise between what's possible and what's perfect. And you know, in the end, it was our site was deemed to be the best for a whole range of reasons. Also, I think what we did was we put together a fantastically good bid, because we got the best people doing it technically. And in the end, there was a compromise, because Australians were deemed to put so much work into it that to lose them in the project, we would potentially lose technical capability, goodwill, a whole bunch of things. And so at this stage, we're very happy with working with them, because they bring a huge amount to the project. So the way that it's shaken down, we're ultimately very comfortable with. Hundreds and eventually thousands of mid to high frequency 15-meter dishes will be located in South Africa and Africa. A bit like that, those meerkat dishes up there. But I don't know whether we've got a picture of the Chinese prototype. It looks very much like those ones, also a Gregorian offset. Those are not 15 meters, those are 13.4 there, so the actual ones are slightly bigger. And then hundreds of thousands and eventually up to 1 million low-frequency antennas will be located in Western Australia. Organisations from 10 countries are members of the SKA organisation: Australia, Canada, China, India, Italy, New Zealand, South Africa, Sweden, the Netherlands and the UK, with many others kind of flirting with the idea of joining. I think they'll join the International Treaty Organisation when it's formed, not necessarily the organisation before the treaty organisation is finally formed. Headquarters is in Jodrell Bank Observatory near Manchester in the UK. There was a competition also for the headquarters. Italy was a bidder. Ultimately, the decision was that the Jodrell Bank, particularly because of the depth of UK astronomy and what was then being offered by the UK government, was a better prospect. It was interesting that it was almost a confluence of positive circumstances for the UK, because George Osborne's constituency, George Osborne, you may remember, was Chancellor of the Exchequer in the UK in the Cameron government. When Cameron left, he left. But Jodrell Bank fell within George's constituency, and he had the purse strings in the UK. So I think that was also something which worked in the UK's favour at that time. Also, there are, I think, over 100 organisations and companies from 20 countries participating in the design and development of the SKA via a whole range of work package-based consortia. There's a dish consortium, for example. There's a signal and data transport consortium. There's a correlator signal processor, science data processor consortium, etc. And so those companies are clustered around the delivery and design of those particular work packages. SKA being developed in two phases between this year 2018 and the late 2020s. Phase 1, Australia will host the low frequency instruments, more than 500 stations, each containing 250 approximately individual antennas, while South Africa will host an array of some 200 dishes incorporating the 64 dish Meerkat telescope. By the way, we've lifted our final dish some time ago, October last year, I think, and we're going ready for this final drive towards the end of this month, where we'll have a functioning 64 antenna array telescope with a working correlator, imaging, etc. It's one of the performance targets we've set for our guys and girls to deliver this telescope. It was at some point, and by my judgment, drifting a little bit, and so we decided to bring in the performance-based target, which I think has worked phenomenally well in getting us all to pull together to deliver on what's quite a hard technical goal. We will start in Meerkat doing science observation almost immediately. There's already a Meerkat paper which has been accepted. But we're really going to begin in a month's time or so, building up. We're still going to be in the commissioning phase because realistically it doesn't all just happen in a big bang, excuse the pun. Commissioning happens gradually, you patch up mistakes, and for several years I think we'll be working with a telescope that's not completely perfect. The SKA itself, it's always much harder to bring a project together where there are lots of different players. You know, we had the money from our government and we had one set of decision makers, so it was kind of easier. If you've got 10 or more countries involved, there's always stuff. You know, different countries have promised different things to their governments. They want this package, the other one wants the other one, and so the biggest challenge is actually organising all of this stuff as opposed to solving some of the technical design questions. So tentatively, SKA should already start producing the science in 2023. Obviously, Meerkat will be doing it from now until then. But anyway, that's the target. Now, what are we looking at? And I know I'm not talking to a general group of people here. You have specific astronomy interests, so apologies if I appear to patronize you. How sensitive will the SKA be? Well, current radio astronomy techniques can detect planets orbiting nearby stars. Phase 1 of the SKA, if, for example, there were airport radar signals on those stars, I'm not saying they are, but if there were, then SKA-1 should be able to detect such radar signals using the instrument that's designed for the first phase. Phase 2, if the people operating those airport radars were also using television broadcasting, you'd be able to detect those broadcasts from those nearby planets. So that's the level of sensitivity that you're talking about. Now, it's all quite complicated, all these different phases. Why did we do it like this? In 2004, once we decided to bid, now we were very much the underdog. We had to bring these posses of astronomers out from all over the world who were kind of only dimly aware of Africa, let alone South Africa. And we were at a distinct disadvantage in this bidding process. I mean, Australia had a very strong history of radio astronomy. Our history is very strong in optical astronomy, but radio astronomy we were always a bit behind the curve until now. And so we felt that we had to demonstrate our engineering capability and build up our scientific human capital. So we figured the best way to do this would be to build our own array. And having our own array would also mitigate the situation if we were to lose the bid, because at least we'd have something. And so we, according to our basic engineering philosophy, we proceeded, first of all, with one antenna, the so-called XDM demonstrator up at Hartgrau, fiberglass. Then originally we decided to build a 20-dish array, which would later be integrated into an 80-dish one. But then we said to ourselves, well, we don't know how to do this. We're finding our way. So we think that we should actually have a smaller, standalone engineering testbed array that won't be integrated into the final design, because we are sure that we're going to make mistakes in Cat7. And we made a number of mistakes, and we've improved everything since then to go to Meerkat. There's a big image of Cat7 there. Well, some of the mistakes were and I'll get onto that in a minute, we're having it center fed as opposed to offset Gregorian. Our receivers they keep on breaking. The cooling system is not optimal. There are a bunch of things that really would have made Cat7 substandard in terms of being incorporated into an SKA design. So we sized it down from 20 to 7, and the 7 was really just so we could demonstrate our capabilities with an array and a correlator, etc. And the key criteria would be sensitivity, good dynamic range, good spectral spatial resolution, and low cost. And we also decided not to do this at Hartbeespoort in Gauteng. We wanted to do it in the Karoo so that we could demonstrate what happened under the Karoo conditions. So even though the Cat7 array, not primarily designed, built for science, and it has ended up doing some science, and as I said just now, the most important lesson from CAT was what to do and what not to do. By the way, CAT, for those of you who don't know, stands for Karoo Array Telescope. And 7 because there's 7 of them. And as I said, some of the Cat7 designs were specifically not adopted for Meerkat, but this is a victory because it saved us a lot of money, and I think those mistakes have been fed into the DISH consortium and other consortia, so that better choices are now being made, were made for the Meerkat technology and will be made for SKA technology. So a decision to move towards a Gregorian offset. Can we see the image of that? Meerkat.
Meerkat.
Yeah, the Gregorian offset, not the center field. There, that's fine. And you see the sub-reflectors there. Maybe I should take a pointer. Sub-reflector. What happens is that the radio waves strike the primary dish. They are then focused on the sub-reflector and then reflected down there to the receiver. And the advantage of that is that the whole dish is then available for collecting, because what happens with the center-fed antenna is that all that stuff in the middle gets in the way and you lose 20-30% or so. And also, given that it's kind of a funny shape now, there's all the stuff in the middle, you've got to do some smart things with software to kind of get the stuff in the middle out of the way so that you can do the imaging in an uncluttered manner. So, to cut a long story short, with this particular design, we were able to reduce from an original design of 80 antennas, 13.5 meter diameter, we were able to bring it down to 64. And there was that 20% gain in sensitivity to give us the same sensitivity because we had a larger collecting area because you didn't have the center-fed clutter in the middle. At the heart of this system, also the receivers. You can't see them there, but they kind of sit underneath the sub-reflector. It's quite hard to see exactly what that dish is actually focused on because of the trying to work your way through the reflector and the sub-reflector and where they're pointing. But if you take a line from the bottom of the main reflector and you take that through the top of the sub-reflector, you project that, that's actually what it's focusing on. It's not easy to work out, but take it from me. As part of the development, we brought in a Stellenbosch-based electromagnetics company called EMSS into a shared risk arrangement. We put some money into them, they put their own money in, and they've now become the world-leading developer in radio receivers. They've built us all the L-band receivers, building the UHF ones. So ultimately, working with private industry in South Africa, and there are other examples that I can bring too, but I'm just mentioning EMSS because it's a particularly successful one. We've enabled having, together with the larger collecting areas and the better optics of Gregorian offset, 4 times better survey speed, in fact, effectively giving us much more telescope for the same price. Max Planck Institute in Germany, they were very impressed by this, and they've now invested 11 million euros into building S-band receivers, which will also be installed on the telescopes, on the antennas. We in fact have space for 4 separate receivers on each antenna. They can be rotated into position very quickly. At this stage, we haven't gone for putting the 4th one in because of time and cost. So there are 3 of the 4 spaces that will be occupied. we could have space for another one. Originally there was the idea to do higher frequency X-band, but we haven't gone in that direction. There's a compromise was made on the baseline of Meerkat. We decided to have a more compact design, particularly useful for pulsars. So the baseline is 8 kilometers, but the SKA phase 1 itself will go out to about 130 or so, 250. And ultimately, the Meerkat will be integrated into the larger array. When it starts operating, Meerkat should become a gold standard in terms of sensitivity in UHF, L and S bands. And what is really essential here is the partnering of the world's entire telescopes across the electromagnetic spectrum so that we're able to observe using multi-messenger astronomy. We're cooperating with SALT, with LSST, and hopefully also with the gravitational observatories to integrate into the global multi-messenger system. We've had a whole range of international astronomers applying to use this instrument. I'll explain a little bit about the different bids for telescope time in a minute. And we're confident that Meerkat will have 5 to 6 years for its science program to be carried out. Of course, this is always a robust discussion with Manchester, because they've got a particular time schedule that they will insist on integrating Meerkat into SKA1 in. We would like a slightly longer time. In my view, because of the complexity of managing all of these international players, there will be the time to do it. There was a call for Meerkat observing proposals by SKA South Africa back in 2009, and these resulted in 10 large survey projects. Why did we do this long ago? Well, the Australians were doing it. And so in order to, as almost a way of advertising ASSA, which is their equivalent of Meerkat. And if SKA Mid was going to be built in Australia, ASSA would have been integrated into it. And so they wanted to advertise their capabilities, and given that they were doing it, we decided to do it as well. So in a way, we advertised the capabilities of the instrument before we knew exactly what they would be. And so there are X-band projects that were submitted, and we don't have an X-band. So they're fortunately very understanding, and they know that now. And so, I'll explain in a minute, but of the original 10 large survey projects accepted, we only have 8 left because we're not doing X-band. So, yeah, maybe we can put up the names of the projects. Yeah, I mean, we've got, looking at the distant universe with the Meerkat array, that's Laduma, they've all got nice names. MALS, the Meerkat line absorption line survey, Fornax survey, MeerTime, which is one of the pulsar timing projects, Mongoose, observing southern emitters, Mighty, Meerkat International Gigahertz tuned extragalactic exploration survey, Thundercat, and TRAPPIST, another pulsar survey. So these 8 large survey projects revised their plans, and they were reviewed in a multi-step process that resulted in a report from a review panel chaired by Dale Frail of the NRAO in the US. And the recommendations of this panel resulted in me selecting a range of rank-ordered large survey projects and components. So those are they. Obviously, making decisions like this doesn't make you popular, because some have higher priority than others, but ultimately through the science committee, which has now become the user committee, using the wisdom of South African astronomers and international astronomers, we were able to kind of settle everyone down to agreeing that this is what we were going to do. So these large survey projects will be allocated 2/3 of the Meerkat science time to be scheduled for projects selected through competing calls. The South African Radio Astronomical Observatory, SARAO, will endeavour to schedule as much of the requested telescope time as was recommended by the review panel, but obviously stuff happens, antenna go down. Operating a real array is different from doing it on Excel spreadsheets. So, you know, the array will be managed dynamically, and obviously with the standard that we're shooting towards of having the recommendations of the review panel achieved. We haven't made specific time allocations, as I've said, but there'll be a substantial share of the overall required observing time, which will be already scheduled starting in 2018. There'll be an open time. 30% of the time will be for new proposals, not large survey projects, but smaller requests for smaller amounts of time. And we've been able to free up this additional 30% through the increasing, through the instrument performing beyond spec. In other words, an increased performance in survey speed, sensitivity, etc. And 5% of the available observing time will be allocated for the managing director to make a discretionary call on. In other words, if something really smart, really amazing suddenly presents itself, you can say, okay, we're going to do that. Because to be hamstrung by bureaucratic decisions that are taken 5 years ago, given the speed that science moves, that's not smart. Now, almost getting to the end, data processing. Data generated by the telescope will be delivered by an optical fiber network into a data center near the telescope site. This data center was designed and built such that it reduces radio frequency interference produced by the computing infrastructure that it houses. In other words, that's a big mouthful. What it really means is that the data center is in a Faraday cage. And this was an interesting challenge for South African construction industry. It's the first time anyone had built a Faraday cage from one of the big construction companies. And you know, clearly your computing system, your correlator, is interfering with the very observations you're trying to take. And so nothing can leak out. Similarly, we decided to put the digitizers, instead of sending an analog signal all the way back to the data building, we digitize that signal right up on the antenna. And clearly the digitizer itself generates radio frequency interference, so you've got to shield it. And so they sit in these big clunky looking boxes where nothing leaks out. So the data is correlated such that the data from multiple antennas appears like data from a single large antenna. What does that mean? Well, in an array, the basic unit is a pair of antennas which gives you fringes, interference fringes. And in an array of n antennas, you have a half n times n minus 1 pairs of antennas. And to make sense of all of those sets of fringes, you have to take the optical path length between those antennas and the central correlator into account, because otherwise you get rubbish. To add all those up coherently lies at the heart of what a large array like Meerkat is, like what SKA will be. And you need then to keep time very accurately. So we've got a maser clock keeping time. And that maser, there's 3 maser clocks, in fact, one which keeps time individually for the antennas, one to link them together, and one to link them up to the time standard, the global time standard. And the drift allowed in that maser clock is a nanosecond in 10 years. So, yeah, that's what's impressive about radio astronomy is this high tech. And also, what we have there in that Karoo processor building, the KAPB as we call it, is what's currently the fastest computer in Africa. It's a single precision, highly targeted machine, targeted at the problems it's trying to solve, single precision using graphical processor units as opposed to CPUs. And the great thing about it was that we had the in-house expertise to build it. Obviously we didn't build the components, but the architecture, the integration, which is all of the stuff you pay mega bucks to your Crays and IBMs and whatever to do, we did that. And so, to give you a benchmark, the speed of the computer is 1.5 petaflops, which makes it at the moment 75th fastest in the world, fastest in South Africa, fastest in Africa. The one just down the road at the Centre for High Performance Computing in Rosebank, that's 1 petaflop, we're 50% faster. And to give you an idea of what the integration costs you, that machine cost off the shelf a bit over 200 million, the one in Rosebank. Our one, which is 50% faster, cost 36 million, excluding the salaries of our guys. So, it just goes to show that if you have that in-house expertise, you can save a huge amount. Obviously, the big panic is losing your people at the end of a project, because how are you going to maintain them? So that's something that's a challenge one has to obviously address. Okay, the science data processor subjects the data to 4 main operations. Radio frequency interference, which is your big enemy in radio astronomy, just like light pollution is in optical astronomy. You've got to find some way to flag that radio frequency interference certainly at a minimum, but hopefully ultimately you can find some way to scrub a lot of it out. You learn the shape of particular signals, you know when they come, what they look like, and then you subtract them out if you can model them, simulate them. We in fact have established a machine learning group in our organization, and the first challenge I've targeted it at is to find ways to more rapidly flag and remove radio frequency interference from the data. Obviously, you want to get on and do sexier things later, such as correlations between real scientific observations that humans would never have picked up, etc., etc. But we want to start with the bread and butter stuff first. Data about unknown objects of interest are calibrated against data about known objects. So in other words, you've got a whole lot of data patterns that you know come from particular objects, pulsars, different classes of galaxies, and you can then match what you see against those and then pick them out rather than doing it by eye. The data is then synthesized to produce visibility data, and this is ultimately our science data product that will go through along the internet to an archive located at the Centre for High Performance Computing here in Rosebank. We're hoping to restrict the bandwidth that we need to about 10 gigs. So, ultimately there is far, far more coming out of the correlator. You've got about a petaflop an hour or so coming out of the correlator, which is in fact roughly about the same data rate as CERN. I think we're a bit faster than them. We're 24 petabytes a day, and they're, I think, 20 or so. But they're roughly the same. Anyway, from the Centre for High Performance Computing, this data is then available to researchers and astronomers for analysis and deriving real science. You've got, of course, the Institute for Data Intensive Astronomy at UCT, University of Western Cape, directed by Professor Russ Taylor, who's heavily involved in that. But ultimately, the owners of the data, owner of the data is us primarily, but then we give it to the principal investigators of the projects, and they can give it for processing to their own institutes. That can be, and there's some Australian PIs, there's South African PIs, but they make the decision as to where the data goes. The IDEA is offering to be part of that value pipeline, but ultimately the decision is the PIs to make. These data products are governed by exclusivity contracts where the PI is involved and we're involved. And once there'll be an exclusivity period, once the period expires, and we're looking at 2 years, the data products will be made searchable and accessible to the public to download for their own use. It's also taught us a lot, this data processing approach, about how to design and implement the science data processor for the larger SKA. we might think as astronomers that we're smart, but actually we've never seen this amount of data before. And one of the failures of these big telescopes could be that technically they work fantastically, but you've got this torrent of data that's coming out, and the people who requested the data don't know how to handle the volume. And that's certainly something which we see we need to apply our minds to very, very actively. And that's why we've enlisted others in the research community, industry, to assist. We've got IDEA, which has managed to raise 30 million rand of its own money outside government through universities to assist in doing that. Now, to change tack away from the technology and the science to a public understanding of astronomy and outreach project, which is a partnership between the National Radio Astronomy Observatory and ourselves, we collaborated to establish the Multi-Wavelength Public Participation Program, or MAP. The National Radio Astronomy Observatory in the US established the National International Non-Traditional Exchange Program, called NINE, all these acronyms, which is aimed at using bilateral partnerships to develop human capacity in radio astronomy and other essential science, technology, engineering, mathematics fields required to build, innovate, and operate radio astronomy facilities in developing countries. This overall objective of MAP 9 is to advance the public engagement with astronomy, as well as the science engagement sector in South Africa, by training high potential members of the sector in project management and using the processes of co-design and cooperation and competition to develop public engagement initiatives or services that will result in real shift within the sector. So in other words, to endear what we do to the broader public and to young people. I'm looking at this group here today. You're all about my age, roughly. And that's, there's some who aren't, but mainly. And we need to change that. We call this project M9, just the numeral M, it's over there, MAP 9. Started at the end of February this year, and the participants will be presenting their phase 1 implementations. I'm not going to go into all the phases, we don't have time. At the SciFest in Grahamstown during the current week and next week. ASSA, this association, was represented at the MAP 9 Development Laboratory, and we did an interview with the Bloemfontein ASSA chapter when the group travelled recently through the Boyden Observatory. So we're looking forward to collaborating with the sector in the future and also continue to be involved in the science engagement activities of SKA in general and the astronomy community broadly in South Africa. Look, I've rambled my way through a rather personal and short account of astronomy in South Africa, my role in it, how we got to where we are, why we're as lucky as we are, and contextualize this within recent science policy developments in South Africa. And I hope this has been of interest to all of you here this morning. I'm now at an end. Thank you very much for listening.
Thank you very much indeed, Dr. Adam. Would you like to answer a few questions?
I can.
Yeah,
Check the time. Where's the time?
No, we've got plenty of time. Dr. Adam has to leave at perfect time to catch an aeroplane to go to Port Elizabeth.
Yeah. Aren't many airplanes to Port Elizabeth?
Anybody have a question? Yes.
So my personal research interest is solar system science, specifically near-Earth astronauts. So I don't know much about radio astronomy. I know that they do observations of astronauts with a receiver for that need to transmit. Is there science space for doing that? Can you, for instance, transmit with a receiver or receive?
You mean bouncing it off? I think it would be possible.
But is that
I haven't seen it, I haven't seen that as a proposal. And I can't think why it wouldn't be, but I mean, it's, I can ask, I think our chief scientist is I'm a nuclear guy originally, so our chief scientist is probably in a better position to answer that question, Fernando Camillo. I don't think any of the current survey projects cover that. However, there is a possibility for another window for projects to be proposed. That was the 30% additional time that I mentioned. But technically, I can't see that shouldn't be a problem. I guess it depends on the frequencies. I mean, we're looking at UHF and LNS at the moment.
Any other questions? I have a question for you. The mean time multi-second, millisecond pulse monitor, is it going to be possible that the air some obstacles?
Yeah, I think you need to talk to the PIs for that, but I think that would certainly, the whole mood in the community is multi-wavelength, multi-messenger, so that if you can propose value, you can share it.
Thank you. Chris?
Just a question about picking up radio signals, radar, etc. from neighboring solar systems. Are you talking 5 light years away, 20 light years?
In that sort of road, not much further away than that, the close ones.
When are you going to start taking holes and actually building the SKA as opposed to taking over near capital?
SKA, well look, we are thinking of building it. I mean, the designs are pretty much finalised.
Is the money together that you need to get started?
Not all of it. And so as a result, what we've got is a design baseline for SKA1 and then a deployment baseline, which is consistent with the design baseline. So, in other words, in the case of SKA1 mid, there's a core and 3 spiral arms. What the money that we have, the way that it's been divided up, you would need to chop off the last 3 antennas. In other words, the ones on the outer antennas on the 3 spirals, bringing you down from 133 to 130. But you would then be able to, at a later stage, put in all the infrastructure and put the antennas there. So that the idea is that rather than wait for all the money, and also the feeling is that once the momentum starts, more countries will come in. So I certainly think that the idea of a deployment baseline was a great step forward because it actually enables you to do something. So ultimately what it means is that the longest baseline reduces from 150 to 120 to do that.
How secure is the financial base in the far future, say 10 years, given the changing priorities of the world economically, politically, and environmentally now, which all seem to be shifting rapidly away from the certain times?
That's not an easy question to answer. I mean, 50 years, none of us know what's going to go on, and this is an instrument designed for 50 years. You can ask the same question for ASSA, for CERN, for anything. So those questions are certainly not questions that will deter most of us. Maybe that's irresponsible. We're kind of passing them back to our children. But that's the best we can do. It's not an easy question. Not possible to answer that question.
Well, thank you once again, Dr. Very